Thanks, Cody. And thanks, organizers, for inviting me here. So my real name is, my first name is Tiangang, my last name is Cui, and mostly Cody they butcher my name, so that I prefer people call me TC to make my life easier, also make your life easier. So today I'm going to talk about optimization-based sampling for hierarchical inverse problems. So basically what our goal is, say we want to convert optimization methods that people develop for to finding the map of the posterior distribution. We want to convert that into posterior samplers. And we also target on Bayesian inverse problems. In particular, we're also interested in estimating some hyperparameters in the Bayesian inverse problems. That's how I come up with this title here. So this is a joint work with Jonathan Basley from University of Montana and Yusuf Mazouk, who just gave a talk, and also with Zheng Wang. Zheng is a PhD student at MIT, and Zheng basically working with Yusuf and I. So basically in this talk, some of the fundamental idea was set by Jonathan Basley in his early work, and then later we found a computable way, so we can generate optimization, we can efficiently compute optimization-based. We can use our convert optimization method into posterior samplers, and also we did some analysis on that. So now we are working on various extensions of this approach. Okay, so let's start. So we already seen a couple talks in the first couple of days about inverse problem and also Bayesian inverse problems. So here, just to put everybody on the same page, I will just briefly review what's the Bayesian inverse problem and what kind of problem we care about. So generally speaking, in many problem science and engineering, we normally build mathematical models or PDE models to understand some physical systems. So in this process, normally we have the PDE model have some driven factors. We call the driven factors the parameter x. So those are the primary variable interests. So and also those parameter x, normally we don't know what's that. Maybe some coefficient of PDEs, or maybe some boundary conditions or initial condition of PDEs. So what we do know is that we can collect some observables of the system, basically denoted by y here. So we also know that the primary variable x and the observable y, they are related indirectly through a solution PDE model denoted by this denoted by the function f here. So in the process, we may also have some noise, maybe a measurement noise or model error. So we denote that by e here. So here we use additive noise, but in general, you can think you can have any noise. Okay. So there's a few features in the setup. One is that the data is not, in general, data is very limited. So either say the data being collected at some sparse locations, or the data is very noisy, and in particular, data is indirect with parameter x. Okay. And also in this setup, in general, we are interested in the primary variable x we are interested in is very high dimensional. In general, we're thinking that kind of discretization of some spatial temporal functions in space or time. Okay, so that's because of discretization of parameters, discretization of functions, so that can be very high dimensional. So basically, through the talk, we also assume that this operator f, this function f, is differentiable. Okay. So in this whole setup, we are interested in this. So now let me show you some of the motivating examples and how this setup can be specified. All right. So first thing we care about is the particular application in geothermal reservoir modeling. And also you can think about in the oil reservoir modeling, gas reservoir modeling, have very similar set of physics. So what we have is basically say, we want to know what's the flow rate underground in the subsurface. And the flow rate of the basically oil or hot water or gas, those flow rates basically being characterized by rock properties. For example, permeability and porosity. Both permeability and porosity are spatially heterogeneous functions. Also in this process, what we can observe is basically we can drill a couple of wells into a reservoir. And then through the wells, we can measure the flow rate, we can measure the pressure, we can measure the temperature. So from the sparsely located wells, we want to reconstruct the rock properties. So also in this process, we have to solve a set of coupled multi-phase non-isothermal Darcy's flow. So basically, this set of equation model how the given particular set of rock property and how the fluid will move across the reservoir. Okay, there's also some highly nonlinear interaction between multiple component fluids. So normally, once we're given those observed data from well bores, once we are able to reconstruct rock properties, then we can make a forecast, say what's the average flow rate, or how much oil, how much gas we can get out of the reservoir. Okay. So this is one particular setup. So another particular setup we look at is polar ice sheet flows. So in this scenario, we are interested to know, we want to know how much ice will flow into the ocean. So this way we can figure out by the amount of ice flow by predicting the amount of ice flow into ocean, we can figure out what the potential sea level is. So eventually that basically is a quite big environmental problem we care about. So in this scenario, basically we build a PD model based on non-Newtonian Stokes equation. So what we can observe is basically the velocity measurement of ice sheet at the top surface. Basically by running satellites, running airplanes, we can measure the velocity at the top surface. And what we don't know about, or the driving factor of this system, is the bottom boundary conditions under the ice sheet. So basically using the velocity measurement on top of the ice sheet, we want to reconstruct the underneath the bottom boundary conditions. So this way we can predict in the future how much of the amount of ice flow into the ocean. Okay. So in all those in those both examples, what we can see that basically we have very sparsely measured data, and the data are indirect to the parameter interest or the driven factor system. So this way basically say that a lot of combinational potential, lots of feasible driven factor system which driven factor of the parameter x can produce similar match to the observed data. So in this sense, basically to quantify what's the prediction, either in the sense of the future production rate or the amount of ice flow into the ocean. To predict those, basically we have to quantify the uncertainties within those parameters, condition on those given observations. So this entire process can be cast into a Bayesian inference framework. So in a sense, basically we build a likelihood function, basically by evaluating the mismatch between the observed data and the observable model output given for a given parameter x. So we can build a likelihood function, and also we can build a prior distribution. So in this particular setup, because of the problem normally ill-posed as we have an indirect observation, and observation normally sparse. So in the prior distribution, normally we inject lots of smoothing assumptions, or we also sometimes we also inject some structure informations. So there's also lots of unknowns about the structure of the prior and also structure of the likelihoods. So in particular, for example, if we use some smooth prior, like the Gaussian process prior, we may not know what's our correlation length to be put into the Gaussian process prior. And also in a likelihood function, we may not know what's the level of the observation noise. And also in some cases, we may not know some of the parameters of the physical model. For example, so here by parameter, for example, here in the non-Newtonian Stokes flow, we may not know the exact strain-stress relationship. In the subsurface flow, we may not know what's the relative permeability function, so which is parameterized by some lower dimensional variables, but this relative permeability will basically control the interaction between multiple components of fluids. So basically, we can put all those lower dimensional parameters which govern the structure change of which govern the structure change of likelihood and govern the structure change of the prior distribution as a hyperparameter. We denote that by alpha. So in this setup, we care about basically we have some high-dimensional primary variable x. So those can be my rock property, can be my bottom boundary conditions, and also have some hyperparameter alpha, which basically is some either the assumption we use in the prior or the assumption we use in the likelihood, or some modular assumptions. Okay. All right. So now the goal is once we set up our posterior distribution, given likelihood, prior, and also some hyperprior over the hyperparameters. Once we set up this posterior distribution, how can we extract information, or how can we extract solution to our inverse problems? So basically in our setup, because we care about some predictions, so in general we want to summarize our predictions as expectations of some function over the posterior distribution. Okay, so here we have to compute this integration, we have to compute about we have integrated over either both the primary variable x and also the hyperparameter alpha. So here now you can see the difficulty. Basically here the primary variable x is very high dimensional because that's a discretization of some functions. And also we have this hyperparameter alpha. For every different hyperparameter alpha, the structure posterior changes. Okay, so now this gives us so both integrated basically integrating the high dimensional x and also the alpha together give us lots of difficulties. So here our goal is basically we want to do two things. One thing, if we suppose we fix the hyperparameter alpha, say just we have a standard Bayesian inference problem. Basically, we have a posterior here. We have a conditional posterior here. So for fix by fixing the hyperparameter alpha, we want to convert optimization method into scalable posterior integration schemes. So here, by scalable, basically we have two meanings. One is the statistical meaning. By scalable means if we want to use this, we want to use our scheme as an important sampling scheme, or we want to use our method as an MCMC scheme. By statistically, we want to, in the MCMC setting, statistically we want to ascertain rate, or the effective sample size will be independent with the parameter dimension. So it doesn't matter how we change the parameter dimension x, the dimension of the parameter x, the ascertain rate or the effective sample size in either applying the MCMC or in point sampling should be independent with the dimension of the parameter x. So that's one thing about the scalable. So another thing about the scalability is we also want this scheme being scalable in terms of the computational efficiency. By computational efficiency, the computational cost per sample should be scaled linearly or n log n to the number of parameters. It shouldn't scale to anything more than the n square of the dimensional parameters. If you have a scheme that computational scale with more than square of the parameter dimensions, normally if you scale for a very high dimensional problem, that's not going to be applicable. Okay? So this is what we mean by scalable. And also, hopefully, we want to extend the scheme for sampling fixed hyperparameter alpha to sample the joint posterior with jointly with x and alpha together. Okay. So now let's basically this part is still ongoing work. At the time I submitted my abstract, I thought I can finish that by the time I give a talk, but actually it's still ongoing work. I will show you some initial result here. But for those top two bullet points, we almost done everything. Okay. All right, so let's start. So first we consider we have a fixed hyperparameter alpha. So in this way, we are targeting on sampling the conditional posterior. So here, basically, we know the likelihood function, we know the prior, but we don't know this normalizing constant, basically the marginal posterior. Okay. So before we start, we just want to set up some intuition. So here, basically, the goal is to convert optimization method into a transport map. Basically, this transport map has similar structure as Yusuf just talked about, but also, this is very different because our optimization is not targeting on the transform map itself. Because through solving the optimization problem, we want to create, inherently, we want to create a transform map. So given a transform map, you can think about, say, we have a reference distribution. Using a push forward map, basically, we can map the reference distribution to the target. So here, the target means mapping to our conditional posterior. So in a similar setup, if we do have a pullback map, we can basically pull back from the target distribution to the reference. So in the idealized world, basically, say, given the transform map, if we're able to construct the transform map, and either we can solve the push forward or we can solve the pullback, we solve the problem. But in reality, by converting optimization method into posterior samplers, we only come up with an approximate transform map. Okay. So in this sense, basically, if we evaluate push forward, we can get to some push forward that looks close to the target, or here target our conditional posterior. Or if we evaluate the pullback, basically pullback will look similar to the reference, but we miss some feature from either the reference or the push forward miss some feature from the target distribution. So, but here the nice thing about using optimization-based method is that we can use either use MCMC or important sampling to correct for any the potential error either in the push forward or the pullback. Okay, so now let's look at it. So what's the basic ingredient we need to convert optimization method into posterior samplers? So here's our conditional posterior. Basically, the basic assumption we need is only about two things. One, that we require that we can evaluate the log of this conditional posterior up to this nominal constant. So we don't care what our constant is, but we do want to be able to evaluate the log of this posterior. Okay. So this is one requirement. This is one of the most fundamental requirements. The second one is basically say we can evaluate the action of the linear right forward models. So just remind you that in the So in the likelihood function, it involves the forward model. So we want to be able to evaluate the action of this linear right forward model, and also its adjoint. So basically, in the PD constraint optimization literature, or even in the ODE literature, it's very well known how to compute the action of the action of the linearized forward models. So I will not go through that here. So basically, given those two ingredients, we are able to convert certain optimization method into posterior samplers. So basically, the general structure looks like following. Say, using some components of this conditional posterior, and also using a random variable drawing from a reference distribution. So here by reference, we just use a prior distribution. Basically, by combining those two parts, we can come up with a new objective function. And then, basically, by minimizing this objective function, so I will show you what the objective function looks like in the next slides. Basically, so now by minimizing this objective function, we get a sample. And then we can also compute the density, the probability density of this sample. So since we get a sample, we can compute the probability density of sample. Then we can use this sample either in the important sampling. Basically, we can compute this normalization constant, or we can construct a metropolitan independent proposal to run the MCMC. Okay, so how to get this? How to construct such objective function? So what is the procedure will look like? All right. So just one more slide about the basic assumptions. So here we are looking at one particular version of the algorithm called randomize and optimize. So in this version, we do impose one additional assumption, is that the log of the target distribution we want to sample from basically can be written as the L2 norm of some high-dimensional function H. So basically, for the kind of application we care about, so for example, if a measurement noise in a likelihood function is a Gaussian, and also if the prior distribution is a Gaussian. So then basically, as you can see, we can convert such a log posterior distribution into L2 norm of a function H. So here to note ourselves, basically, this function H is a map from, suppose we have n-dimensional parameters and a d-dimensional data. Is a map from Rn to Rn plus d. Okay. So if our target distribution have this form, then basically we can construct the objective function as the following. So first, we can draw a random variable psi from the prior. Okay, so here psi is a prior sample. And then using this high-dimensional nonlinear function H, and also using the help of some matrix Q. So here this matrix Q should have the same range as the linearization. So I use a gradient notation to denote the linearization. Should have the same range as the linearization of this high-dimensional function H. So once we have this matrix Q, then basically we want to solve this equation here. So basically our optimization problem is solving the random variable psi equals this gamma prior square root multiplied by transpose matrix Q multiplied by this high-dimensional function H. So basically just draw another picture so we understand dimensionality of this problem. So basically if we look at the linearization of the function H, it's basically have n plus d rows and n columns. And the matrix Q transpose basically have the n rows and n plus d columns. Okay. So basically here by solving this optimization problem, basically we will create a transformation random variable from a space n to an n-dimensional space to an n-dimensional space. Okay. So now let's look into how can we actually construct such a matrix Q and how this thing looks like. So basically, we first find the map point of the conditional posterior. At a map point, basically, we can compute the QR factorization of the linearized function H. So in our particular setting, the linearization takes this form. Basically, it has a linear form. So that's basically the inverse square root of prior covariance. And also we have the Jacobian or linearization of the forward model evaluated at the conditional map. So once we have the basic here, this Q matrix, we will basically have the same range as the linearization of this function H. Okay. So now basically solving this using nonlinear optimization method, basically it's a combination of Newton CG, truss region, and also if you have bounded parameter space, you can apply interior points. So here basically the key thing that is a very minor modification, because all we need in evaluating this linearization H is a linearized follow model. So also for the same requirement for computing the conditional map is also using this linearized follow model. As soon as we have the linearized follow model and it's adjoint, we can convert, with very minor effort, we can convert the standard nonlinear optimization method to solve this nonlinear equation here. Okay. So another thing about solving this nonlinear system equation, we get a sample x for any given random variable psi. Okay. And then we end up with a computationally trackable way for computing the probability density of this random variable x we got. So here the probability density basically taking this massive form. So the important thing here is that basically the computational cost of evaluating this part doesn't really cost anything, because it's just evaluating a normal vector. But the computational cost here, basically we have to compute the determinant of an n by n matrix. So this is not so nice. And also here, basically, so somewhere down the stream, this guy, the determinant of the prior covariance will be factorized out. So this thing doesn't really matter much here. But the key thing also, another thing that basically this matrix Q here is high dimensional. To evaluate action of matrix Q is not scalable. It's scaled as at least a quadratic with the dimensional parameters. So that's not very nice too. And also seen from this formula here, it's very hard to see what kind of structure we can extract out of this procedure. So now we want to look at different way of constructing such a matrix Q. And this automatically also reveal the basic properties of this randomized and optimized procedure. Okay. So what we do here, so basically look at this linearized follow model. We look at the linearized follow model as the map point. So if we modify that a little bit by basically adding the Weyting transform of the prior cover, of the prior noise, of the observation noise, and also on the right multiply by the square root of the prior covariance. Basically applying some Weyting transform here. So then we can compute the singular value decomposition of this modified linearized fold model. So again here, we never form this metric explicitly. We always use a adjoint method and also the action of linearized fold model. Basically using the action of this matrix, basically then we can compute the singular value decomposition in a low rank form. So computational here basically will scale with the rank of the singular values. Doesn't scale with any dimension, explicit dimension of this matrix. Okay, so that's important. So now basically given this SVD here, so we can rewrite the linearized fold model. We can rewrite this linearized function h in the following form. And actually, we can construct another matrix Q tilde in this particular way. Although the construction of Q tilde looks very messy here, but actually this Q tilde is also has orthogonal columns, and this Q tilde spans exactly the same subspace as this Q here. Okay, and more interesting is that this Q tilde here basically will have the low rank can be represented by a sequence of low rank vectors. So computing action with the Q tilde basically only involves the rank R operation with those low rank vectors. So also another interesting here that if you look at this basis phi, basically the red singular vectors, the red singular vector here touches the parameter space. So using this particular form of singular value decomposition, and also using this particular form of Q tilde derived from the singular value decomposition, we can then rewrite our system equations. So there's a few interesting things here. So one that we can construct oblique projector using the red singular vectors. So this is the oblique projector, rank R oblique projector in the parameter space. By using this oblique projector, we can split the parameter space into two components. So in one component, basically our nonlinear equation becomes a linear equation. It's basically say in the null space of the projector, we want the parameter x to be the same as this prior sample psi we draw. Okay, so that's what happens in this null space. So within the random projector, basically we are assuming this messy-looking nonlinear equation here. So, but basically here, so basically now you can think about, although the nonlinear equation looks pretty messy, but actually you solve that, it has the exactly same requirement as solving the original optimization problem. It's just after few more manipulation in linear algebra. Okay. So the key thing here is that, so now our system of equations can be decomposed into two components. So one component only happens in the prior. Basically, we're mapping a prior sample. In the complement space, we're mapping a prior sample to the actual posterior sample, to the actual approximate posterior sample. So in the Ranger project, which can be low dimensional, we are solving this nonlinear equation here using optimization methods. Okay. So also by looking at the form of this, splitting of parameters, we can also further analyze the theoretical property of the randomized optimized. That will come up later. So computationally, so this gives us a much easier way in operating with in solving this nonlinear equation here, because now we only need to deal with the lower dimensional matrices. So now the solving this nonlinear equation becomes scalable, linear in the dimensional parameters. Another benefit is that in computing this determinant, that happens in evaluating the density of the RTO sample. The computation of the determinant has a low rank form. So here, original determinant n by n system, so now it becomes a determinant of a R by R matrix. So now this part becomes scalable as well, scalable in the computational sense. Okay, so that's all good.
So can I ask a question?
Yeah, sure.
What is the assumption that ensures that is a unique optimum?
So
a unique X, because that's important for your expression for the density.
Yes. So that I will show that in few more slides. Yes, yeah, that's a good question. We do need to impose further assumptions on. We do need to impose further assumption on this nonlinear function G. Otherwise, it may not be unique, which causes lots of troubles. Yes, that's a good question. Okay. So also out of this process, we know. So basically, we have a scalable way to get a sample using optimization method. We also have a scalable way to compute the density of that sample, and also that density is normalized. So those are nice features we got out of this process. So before getting to your question, so let's just look at some numerical example to see how this thing works. So basically so here the one training parameter in the process says what's the rank in this SVD we want to use. So now let's see if we change also this rank of SVD also affects the way of solving this optimization problem. Let's first see in some very easy, simple examples. Let's see how the impact of this rank and see what the structure of the process. So now we have suppose we have a linear model, linear follow model, and Gaussian observation noise and Gaussian prior. This way, the posterior is also a Gaussian. So here the blue contours represent my prior distribution, and red contour represents my posterior distribution. So first, I just set the rank of the SVD to be 0. Basically means we are solving everything in the subspace, and we don't solve this nonlinear equation here. So of course, we just got a set of prior samples. Now we move to anywhere. So if we gradually change the rank of the SVD to be rank 1, so now we know that we are solving so basically rank 1 means pretty much we are constraining our problem to the nonlinear, actually here, so just a different linear solve to this direction here. So that's the shape of this blue contour here represents the shape of the RTO density. So that's the shape of the sample you can get. So now you can see that along this dimension, basically along the null space, we still have the prior samples. But along the rank 1 dimension, we are gradually pushing the prior sample into a posterior. Oops. So this will be when we have a rank 1 project. So now if we change that to a rank 2 project, so now you can see basically all the samples nicely lies in the contour of the posterior. Because here we assume the model linear, so in this case, actually the solution is unique, and also basically in this scenario, the RTO density is exactly the same as the posterior density. If we move to the nonlinear scenario, it's not, so it actually looks more interesting. So here again, if we compute the map, first we compute the map point of this density here, and then we compute our SVD, we come with our projector, then we can solve our nonlinear system equations. So here, if we force the rank to be 0, nothing happens. We just got a set of prior samples. If we force the rank to be 1, so here, basically along this direction, we are solving the nonlinear equations, and along this direction, we are solving. We basically don't solve anything. Basically, it's a mapping from prior samples to posterior samples. So now this is a structural RTU. This is a scatter plot RTU sample that we get. Okay. So basically, you can see along this dimension, with the loss of nonlinearity happens, along the dimension basis, still the prior. So if we gradually move the rank of SVD to 2 dimension, so now you can see that basically we get a set of RTU samples that looks almost the same. I wouldn't say almost, it looks close to the actual posterior, but still have some differences with the actual posterior density. So now we can then apply either MCMC method or the important sampling to correct for any of the potential bias. Okay, so now let's get to the assumption, how this thing can work. So basically, if we look at this decomposed form of the RTU density, basically we need to impose one additional assumption on this nonlinear function G. Basically, if this function G, I think basically the function G itself is literally continuous, so that's very easy to verify. The hard part says the function G needs to be injective, and also the inverse of G needs to be continuous as well. So how can we verify that? Basically, in general, we cannot. So I have to say in general, we cannot. Only say numerically, when we compute the posteriors, numerically when we solve optimization, we will see it's non-unique. But in general, it's very hard to verify this condition here. We are still working on strategies how to verify that and how to get away with this injective assumption. Okay. So anyway, so basically, if I assume those conditions to hold, so then because of the particular structure of the transformation variables, so basically in the null space of the projector, so we have a mapping from prior to posterior, mapping from prior to target. That's just a linear mapping. And within the random projector, this is where all the nonlinear transformation random variable happens. Basically, using the particular structure, we can analyze the infinite dimensional limit. As soon as the rank of the projector, basically, if we look at the truncated SVD, as soon as the rank of truncated SVD converge as we refine the parameter dimension, basically we can show that this ratio, basically ratio between the unnormalized conditional posterior and the RTU density, is going to converge to some positive value at the infinite dimensional limit. So basically, if you look at the ratio, basically this is how we define the metropolitan Hastings scheme. Also, this is how we define the important sampling. So basically, if we apply the scheme, and also in particular, if we have all the assumptions to hold, then basically, if we keep refining the parameter x, statistically, this method should be scalable with the parameter dimension x. Okay. So now let's just look at some numerical example to verify this. So here we are looking at a very simple PD model. It's basically assuming the Poisson's equation. And here the parameter of interest is the permeability field x. So we collect some observation on the potential U at some spatial locations. So here all the data drawn from basically all the data synthetic. And this plot here shows the realization of the true parameter we use for generating data. So this is a true parameter. This is a true permeability field we use. And here, basically, the true potential function computed for this given permeability field. And the red cross shows the location. So here, the x should be s as a spatial location. So here, the red cross shows the location of the observed data and the magnitude of the observed data. And so this curve here represents the forcing on the right. Okay? So this is the basic setup. So the goal is basically using these red crosses to recover this permeability field x, this one-dimensional permeability field x. Okay. So we do field test. So once we draw this random variable from prior distribution, and also we discretize the random sample on multiple level grid. So basically, we want to come up with a different range of the different dimensionality of the parameters. Also, it's corresponding we have a different dimensionality of the random variables. We want to see if our scheme is actually scalable with the dimensional parameters. So this is the first thing we want to try. So the second thing we want to try to say, for a fixed dimensionality of a parameter, fixed grid size, and we want to vary the noise level in the observations to see how the RTU behave with a different noise level. So here the goal is basically can think about if we decrease the noise level, the posterior will become more concentrated. So we want to see that if RTU is robust with the concentration of the posterior distributions. Okay. So now let's first look at the change of the performance with the change of parameter dimensionality. So here basically we have a random parameter dimensionality from 41 all the way to about 10,000. So along this corner, what we plot is the effective sample size of MCMC. So out of 5,000 samples. So here, basically, along here, we are plotting the acceptance rate of the MCMC for different different parameter dimensions. So basically, you can see that out of 5,000 samples, we almost got 4,000 samples, 4,000 independent samples, 4,000 effect samples in the MCMC scheme. And also, this seems almost a constant for different parameter dimensionalities. So now, surprisingly, the acceptance rate is very high, almost 1, and also the acceptance rate is looks almost independent in this example with a parameter dimensionality in this example. Okay, so this is one thing we have. And how does that mean to the importance sampling? Basically, if you look at the variance of the log of importance weights, basically here we also see the variance of weights looks almost like almost a constant as well across different dimensionality. Basically, if we want to turn this into an importance sampling scheme, we also should have a performance robust with the dimensionality of parameters. Okay. So one interesting thing in terms of a number of iterations in optimization to get each sample. So basically, we can see initially with a very low grid size, the number of optimization iterations about less than 100. As we refine the grid, initially gradually increasing, but as we keep refining the grid, basically numerically, our follow model converges. So then we can see the decrease in the number of optimization iterations in here. As we expected, as the follow model converges, we will expect if we keep refining the grids, gradually the number of iteration optimization will stay at a constant level. Okay. All right. So now let's look at some of the reconstructed results. So here, basically, what we plot is a credible interval of the posterior sample, computed from posterior samples for different level grids. Basically, you can see here, using different level grids, we end up with very similar credible intervals here, okay, which is always a good benchmark. So now let's look at what's going to happen if we change the noise level. So now we are fixed the dimensionality of the parameters. We are changing the noise level. By decreasing the noise level, basically the posterior distribution will be more concentrated. So in this scenario, we basically test a various range of a noise level from 10 to a -7, which is a very small noise, to about 10. So here, as you can see that basically both acceptance rate of the MCMC and also effective sample size, in both cases, they are pretty robust with the noise level. But big drawback here is that if you look at number of optimization iterations per sample, basically as we decrease the noise level, we do observe that the number of optimization iteration gradually increase with a decreasing noise level. Basically, one way you can think about that, if we go back to our two-dimensional example, say if the posterior distribution is very concentrated, the cost of pushing a prior sample to the posterior gradually increase because we are trying to use the optimization method to push a sample to a very concentrated posterior. So not surprisingly, in that scenario, so the number of optimization iterations also increase. Okay. So here, basically, some reconstruction result. And it's not surprising again if we have a very high noise level. Basically, the reconstructed posterior credible interval have nothing to do with the actual permeability field. But if we gradually increase if we do have a small noise in the observed data, we do have a very high quality credible interval. Nicely covers the original permeability on the reconstruct. Okay. So basically, from this study, what we conclude is that basically say that the acceptance rate of MCMC or the effective sample size basically is scalable with the parameter dimension, and the variance of the log important weights also scale with the parameter dimension. So the number of optimization iterations stabilize if we keep increase the parameter dimension, which means ultimately it can be scalable as well. However, if we change the observation noise, so the acceptance rate of MCMC and also effective sample size, they all seem scalable with a noise level. But the number of optimization iterations, this is a typo here. The number of optimization iterations increases with a decreasing noise level. So this is something we need to consider in the future. All right, so let's now, in the last couple of minutes, I want to move to the hierarchical sense, hierarchical framework. So here is some still work in progress, and show you some very initial results. So here we basically not only interested in the conditional posterior, we're also interested in the posterior. We're also interested in hyperparameter that controls the scale of the posterior and also the scale of the likelihood. So to begin with a very simple framework, so basically I assume two things. First, I assume we have a parameter lambda to control the relative weight. Basically, this lambda is inverse of the variance of the observation noise. And also here we have another parameter, hyperparameter delta, to control the relative weight of the prior. So this also can be interpreted as the inverse variance of the prior distribution. So for both lambda and the delta, we basically use a gamma distribution as a hyperparameter. So now we want to basically apply the RTU scheme within the Gibbs sampler to sample this joint distribution of the primary variable x and hyperparameters lambda and delta. Okay. So here's nothing surprising. Basically, for any given parameter x, we can just apply. We can basically use a conditional. We can basically use a conjugate prior to sample the hyperparameter lambda and delta. So here we basically first condition on the given parameter x, we sample the hyperparameters. Then, for the condition on these updated hyperparameters, we can apply RTO to sample the resulting primary variable. So because RTO has a relatively high assessment rate, so here RTO can be a good sampler for dealing with the hyperparameters. So sorry, for dealing with the primary variable here. So to show you some quick numerics. So again, we are solving the Poisson equation. We are trying to reconstruct permeability field. So this black line here is a true permeability field I generate. That's the thing I want to reconstruct. So by applying this RTO within Gibbs scheme, so basically we can nicely reconstruct the credible intervals of the permeability field, and also we can accurately compute the histogram for lambda and delta. So here basically also, so this is a histogram of the one particular pixel, the permeability field at one particular location. So basically this is still work in progress, and we will come back to this in the discussion time. So in general, basically if we apply RTO, basically we can generate explicit transfer maps from some reference distribution to a target distribution. And here the target distribution is just approximation to the posterior. The good thing about this RTO density that we know is normalized form. So then, for fixed hyperparameters, basically we know we can also show that basically numerically, and also we can actually prove that this has a dimension-independent behavior. So again, we do have troubles in these restricted assumptions. So in the case if we have a non-unique solution, what should we do? So we developed some idea, but still working on that. Basically, try to convert things like a trust region method to safeguard against this. So one thing I didn't really talk much about is this non-uniqueness also related to. So non-uniqueness is also related to this determinant. If this determinant is singular, then we have a non-unique solution. So basically by building a trust region method, try to avoid the singular determinant, we can avoid this situation, but this is still much work in progress. Oops. So another way, of course, we can also try to develop nonlinear preconditioners, try to deal with this issue, but this will also need some work to look into. And also for sampling the hyperparameters, so actually we know that if we apply the RTU within Gibbs, although our original RTU method is scalable with the parameter dimensions, but if we put that in the Gibbs scheme, so if we increase the parameter dimensions, actually what we can show that this is not dimension independent anymore. Basically, a certain rate, a certain probability a certain probability will be basically collapse to zero as we increase the dimensionalities. So here are a few different ideas we can apply to solve this. One will say basically we're using RTU, we can compute the marginal posterior, the nominal constant of the conditional posterior. So this way we can apply pseudo-marginal to sample the hyperparameters. So actually we test that, and because I haven't got any satisfactory numerical result yet. I hope next time I can show you that. And also another idea, basically we can use a non-centered, basically current version, the centered version of the Gibbs update. We can also try to use a non-centered RTU within Gibbs to help with this issue. And also in terms of future work, so one say basically the RTU gives us an explicit way of mapping sample from reference distribution to a target. We can also think about either instead of mapping Monte Carlo points, we can map in QMC points, or either we can also map the, say, the quadrature point. This way, maybe it may help in certain scenarios to improve the quadrature accuracy. And also we can apply multi-level, actually very natural apply multi-level method here when we can further accelerate the optimization, or we can also achieve the variance reduction using multi-level methods. It's just a very, very natural apply the multi-level idea here. And the big thing that how can we extend this to non-Gaussian likelihood and possibly also non-Gaussian prior? So basically, in some scenario, we can transform likelihood function and also prior distribution into a Gaussian. So in those scenarios, we can deal with the non-Gaussian likelihood and non-Gaussian prior. But in general, can we find a more explicit form of dealing with the non-Gaussian likelihood? So that's a question we don't know yet. And of course, we want to push this the existing method into application in subsurface, and also the polar ice-sheet flow I showed in the first two slides. So also, it'll be interesting to see if you have any application, either SD or OD, or even some regression models. Maybe interesting to see how the RTO method can be applied to that scenario. If you're interested, please talk to me after the talk. All right, I think I'm just on time. I will stop here.
Okay, we have time for questions.
Yeah.
Perhaps my question relates to your third dot point, but I was going to ask, how important is your omnitive noise to what you're doing?
So,
you have intrinsic non-Gaussian data and not.
So currently our trouble that because the current form of the transformation variable, depending on that if we only applies if we can write the log of the target as some L2 norm. So I think one way to deal with that, say the inner no-brain will deal with that, say it doesn't matter what my likelihood is, I approximate that by a Gaussian, and then still write that as an L2 norm and apply the scheme. But a much better way to say instead of relying on this L2 norm, can we find something else to basically can deal with that implicitly, not doing this direct approximation using L2 norm. Yeah. So I think for our application, in general, say either in the polar ice sheet flow or the geothermal oil reservoir modelings, normally the Gaussian noise works pretty well. But in many other problems, like people may deal with logistic likelihood or Poisson likelihood, then actually look at those different likelihood functions within the scheme can be very useful. But also the nice thing about RTO is that it's not really, say, in overall save how much computational time it saves. It's basically this method embarrassingly parallelizable. So if you have a cluster, you have a computer on cloud, you can just, on each node, you just run individual optimization problem, you got samples. So it doesn't rely on sequential form or MCMC. I think that's a really interesting part of extending this into different scenarios. Okay. So it's very similar. The randomized maximum likelihood doesn't have this Q here. It just has random perturbation and random optimization. It turns out very hard. Initially, it's almost impossible to figure out what's the density out of the samples from randomized maximum likelihood. And lately, there's a recent paper by Dean Oliver. After some other modification of the posterior distribution, they come up with the sampling density of randomized likelihood. But the trouble is that to evaluate that density requires the Hessian of the posterior. But the Hessian of the posterior itself may not be positive definite, and actually very likely the Hessian is a singular matrix. So then basically means that density doesn't exist. So I don't know how to deal with that. Maybe the trust region method we are trying to apply here can also help in that scenario, but we haven't looked at that yet. Okay.
So you don't need the second derivative?
Yeah, so here basically all we need is, say, the linearization model. So that's all we need. We don't need the second derivative. That's important. So normally computing second derivative using adjoint is not that big deal, but really say what the proper second derivative may not be compact. So that can be really problematic. Okay.
Okay. How do you deal with local, when you solve a problem, for example, by minimizing, solving the non-linear equation,
yeah.
sometimes you end up with a normal solution.
So as yes. So I think there are two. Basically, I can split your question in two parts. So first, if you look at the form of this optimization problem, so we don't really need a map point to compute this Q. So in theory, any Q matrix can work. It's just say which one the best Q matrix. Actually, we can show that the optimal one shouldn't be this optimal in the KL divergence. It should be this point evaluator map, just because we can do it and it seems a good approximation. You can grab any random sample from a posterior or for even adaptively. You can grab any Q matrix that will give you a valid map transformation of random variables. So that part is not a big problem. The big problem that if we actually solve the optimization problem, if we run into local minima, what will happen? So basically, if we believe the solution is unique, okay, I think I know how to do that. Basically, we have to solve this equation. So if we run into local minima and the solution of this equation doesn't hold, we should discard the sample and keep searching. So, but if we run into multiple local minima and we do have multiple solutions, then we run into trouble with the RTO density no longer valid. We do need to do either say trust region or some other rejection method to safeguard against that. So the key thing that we really need to solve this equation here. So in the sense that basically say we should avoid it automatically by default, we should avoid the problem of local minima. And local minima, the equation must hold. Okay.
Okay, I'll suggest since we're over time that we save the other questions for the break. And thanks, TC, again.